Our next speaker is Dr. and Professor Dacheng. The title of his talk is More is Different. ViTAE elevates the art of computer vision. Professor Tao is the inaugural director of the JD Explorer Academy, and he's also a senior VP of JD.com. He's also an advisor and chief scientist of the Data Science Institute in the University of Sydney. He mainly applies statistics and the mathematics of artificial intelligence on data science, and his research is detailed in one monograph and over 200 publications in prestigious journals and top conferences. He received the 2015 Australian Scoopers Eureka Prize and also 2018 IEEE ICDM Research Contribution Award. And as well as the 2021 IEEE Computer Society McCloskey Technical Achievement Award. He's a fellow of IEEE, ACM, AAAS, IAPR. He's also a fellow of the Australian Academy of Science, the World Academy of Science, and the Royal Society of NSW. So without further ado, let's welcome Professor Tao. Professor Tao, please.
Okay, so thank you for your kind introduction. Hello, everyone. This is Dacheng Tao. I'm delighted to receive an invitation from the forum to introduce our recent research on super deep learning, otherwise known as a foundation model. Quite a while ago, large-scale neural networks received a lot of criticism because the training of such networks is costly in terms of computational resource, power supply, and also data. So given these negative perspectives, why should we and many major research entities continue to follow this seemingly very challenging wrong way? Today, I'm trying to bring some not yet mature theoretical evidence and some solid empirical evidence supported by innovative algorithms and models. I hope that within a period of time, maybe the next 5 to 10 years, more people in both academia and industry can embrace super deep learning or foundation model in different ways. To foresee the future, it may be helpful to first know the history. Although AI and neural networks are very young comparing with mathematics, physics, statistics, and chemistry, in the past some 80 years, a lot of interesting things have happened. Over these 80 years, AI has experienced rapid development through 3 or even 4 enormous waves from crafted knowledge-based intelligence to perceptual intelligence, and then context intelligence, cognitive intelligence, and very recently known as trustworthy artificial intelligence. So as mainly because deep learning-based AI really benefits humans' life, but also brings new problems to think. Those problems are ethics related. Thus, some people humbly think that at the same time, we are also in the fourth wave of trustworthy AI. There are many open discussions about the trustworthy AI, such as how to protect the users' privacy when they share information with companies, how to guarantee the proper use of such information, how to balance the privacy and security of people in the public areas by using surveillance systems, and how to ensure fairness and robustness for AI systems. So here I show a map taken from the internet for linking the historical development of AI and neural networks. I can't mention every important work below, but I will choose to introduce a few very representative ones. And find there is a strong correlation between the waves of AI and those of neural networks. So it is also interesting to read a lot of nice stories about AI and neural networks. So let's first record the development of neural networks. The concept of neural networks was first introduced in 1943 when psychologist Warren McCulloch and the mathematical logician Waterpiece designed artificial neurons inspired by biological neurons. An artificial neuron is the smallest unit of an artificial neural network and can be used for classification problems. In 1957, Professor Frank Rosenblatt, an American psychologist and also a father of neural networks, invented perceptron at the Cornell Aeronautical Laboratory. Based upon neuron perceptron, extends the network input from Boolean to real numbers. He also proposed the stochastic gradient descent algorithm to learn the weights of neurons. I still remember that at the same time, some book even had a very loud slogan saying that AI is dead, long live neural networks. So although the perceptron itself is very simple in structure, it marked the beginning of modern neural networks. At that time, New York Times highly reported this simple algorithm and presented an extremely high expectation on this algorithm, such as this embryo will eventually enable machines to walk, talk, see, and write. But around the same time, maybe a few years later, Frank himself also found that this single layer network neural perceptron cannot sort out the XOR problem, but he assumed or he insisted that networks with multiple hidden layers can really solve this XOR problem. But the problem is that he didn't eventually find a reasonable algorithm to really find suitable weights for those networks with several layers to really address this XOR problem. One more thing, we also know that there is an IEEE medal named after Frank Rosenblatt. So 10 years later, in 1969, Marvin Minsky published his seminal book, Perceptrons, An Introduction to Computational Geometry, which pointed out that perceptrons cannot solve even the most basic XOR problems. As a result, the development of artificial neural networks ended abruptly and stagnated in the study of perceptrons. The stagnation lasted until 1986, when Prof. Geoff Hinton, a father of deep learning, successfully used the backpropagation to train a multi-layer perceptron MLP to solve XOR and even more complex problems. Following this breakthrough, neural networks began to attract intensive attention from the wider community. In 1988, Turing Award winner Professor Julie Pearl introduced the probability and decision theory to the field of artificial intelligence, developing precise mathematical descriptions for computational intelligence paradigms such as neural networks and evolutionary algorithms. At the same time, in the middle 1990s, Professor Wapnick, Jovanakis, and Professor Valiant introduced the Galilean-Cantley's framework to successfully propose the statistical learning theory and the probably approximate correct or PAC framework, which allowed us to effectively correct the theoretical analysis of neural networks and machine learning algorithms, and also allow us to design new algorithms through theoretical analysis. Especially, support vector machines stemmed from the generalized portrait method became a phenomenon in artificial intelligence around the 1990s. In 2006, Hinton published a popular paper reducing the dimensionality of data with neural networks to remind the community about neural networks with multiple hidden layers. Around 2010, due to the emergence of large datasets and high-performance computing equipments, the outstanding performance of convolutional network-based AlexNet in the 2012 ImageNet Challenge marked the arrival of the era of deep learning. In its development over the past few decades, neural networks have experienced both a decline and a subsequent resurgence in popularity as it continues to spiral onwards. After every 10 or 20 years, we encounter a significant leap from a quantitative change to a qualitative change in our research. It has been a decade since the success of AlexNet in 2012. So what are we to expect now? This progress can be summed up as more is different, simpler yet refined. Presently, through super deep learning as well as the foundation model, neural networks have thrived and reached new heights. Driven by the transformer architecture, foundation models represented by GPT-3, DALL-E, and Vision Transformer continue to come to our attention. We can clearly see that the future trend is models with more parameters but simpler design strategies to be more compatible with more data and more modalities, and thus to be more capable of adapting to the needs of downstream tasks. Will the walking scale networks with more parameters make a difference? More is different is the title of a very popular article published in Science in 1972 by Professor Philip Warren Anderson, the winner of the 1977 Nobel Prize in Physics. In this article, he discussed a range of topics from the study of elementary particles to the study of condensed matter physics. He pointed out that as the number of research subjects increases, quantitative changes can lead to qualitative changes. Therefore, we need to use different tools. From Philip's observation, we can expect that super deep learning or foundation model is an important tool to promote the transition from quantitative to qualitative change. So, are we now in such a critical state? So how can we achieve the aforementioned goals? We can see that the growth of data, model skill, and cognitive power has been exponentially in recent years. Specifically, the quantitative data used for our calculations, be it images or text, has reached tens of millions, and it can be expected to reach hundreds of millions in the very near future. Our model parameters have developed rapidly in the past few years, especially following the introduction of the transformer architecture, which has caused an exponential increase in network size. The same applies to computing power, especially considering the close integration of software and hardware. We can expect a very efficient computational platform. More is different. We have now ushered in the era of super deep learning. Foundation model will be rowing the practice and eroding the theoretical research. For decades, every time there was an AI boom, we would say that the technological singularity was approaching, at least in the media, even if it ended up being a joke. This is because it was always very challenging to deploy AI in practice and to use AI in the way people think. However, maybe this time will be a bit different. So let's take a fresh look at neural networks. We can start from convolutional neural networks because AlexNet ignited this wave of artificial intelligence driven by deep learning. In 1998, Professor Yan LeCun and his colleagues delivered one of the earliest convolutional neural networks for handwriting character recognition, which is called LearNet. But it's important to understand that the most important contribution is that they use backpropagation to optimize the weights of the network. There was an even earlier prototype developed by a Japanese computer scientist, but he used fixed weights. The LearN network has 5 layers and was optimized using stochastic gradient descent upon standard handwriting digits. The design achieved great success, achieving an error rate of only 1% when recognizing the digits of the US postcode. While the architecture of the current best-performing neural networks are much more complex than that of LearnNet, LearnNet was widely recognized as a starting point for a large number of neural network architectures and has aroused the interest of scholars in the study of neural networks. As we stack more convolutional layers, the network can become deeper and have more parameters. The many-layered networks is thus expected to have more capacity to fit various types of images and therefore able to attain better performance on various tasks. However, as the gradients are computed by the chain rule, the gradients in the early layers heavily rely on the succeeding layers. Thus, a very deep architecture tends to have a gradient vanishing or gradient exploding problem, which becomes a bottleneck of such design in practice. So we can see the figure here. The skip connections or shortcuts were proposed to bypass some layers to mitigate this gradient vanishing problem. The design stabilizes the training by learning the residual feature representation instead of learning the signal representation directly, and enables researchers to design a very deep neural network, such as ResNet 152, which consists of 152 layers, as shown figure here. Although convolutional networks have achieved great success in image processing and understanding tasks, in the end, it failed to cause an uproar in natural language processing. The main reason is that CNN is good at hierarchical modeling, where natural language processing is more dependent on the modeling of long-range relationships in sequences, and so recurrent networks, RSTM and hidden mark model, was still dominant in NLP before the invention of transformer. However, there are two vital problems in recurrent networks as well as other conventional models. The first is the parallel computing capability of the model is severely limited, resulting in a high training cost in large-scale practical applications. And second, it is difficult to expand the model, which limits the model's capacity. Transformer really changes natural language processing. Through the transformer block, we can easily develop large-scale deep models or super deep models. The transformer block contains a multi-head self-attention and a feed-forward fully connected layer. The self-attention layer generates a contextual representation of each token. By replicating multiple self-attention layers, we have this multi-head self-attention, which is capable to attend to different kinds of information, such as lexicon and syntax. This is because multi-head self-attention jointly attends to information from different representation subspaces at different positions. Self-attention layer plays an important role here. It allows parallel and distributed computation, and thus achieving fast training, much faster than recurrent networks. It captures better global dependencies between words, and it provides better interpretability by realizing the attention scores. Here we also need to know that the self-attention process the inherent disadvantage of sequential modeling due to the lack of positional information. However, this issue can be easily addressed by using the absolute position encoding. This encoding informs the model positional information by simply adding the position encoding to the word embeddings. We can either learn this position encoding or use some predefined calculation. The feed-forward layer can be very wide. Transformer builds a new path in deep learning and brings more and more opportunities. The NLP community has witnessed the greatest success by transferring knowledge from large trained transformer language models trained on the easy-to-acquire unlabeled data, such as there are many typical models such as BERT, GPT, Mactron LM, and T5, where the general language understanding evolution GLUE benchmark becomes a de facto standard to measure the effectiveness of super deep learning models. The figure here shows the relationship between language model size and the GLUE score. The common practice is increasing the model parameters to yield better GLUE performance. All super deep models can be categorized into two groups: the general purpose model for universal tasks and the parameter efficient model mainly for understanding tasks. For the general purpose super deep models, so we can see this blue line. So they are linked with the blue line. Which consider both supervised downstream tasks, zero-shot tasks, understanding and generation tasks. Their universal capacities are not limited to the GLUE tasks. So maybe it can. So some people thought that they were the first step towards the so-called general artificial intelligence at the cost of the larger training cost. Personally, I don't want to use the term AGI. For the understanding task-specific super deep models, see the orange line at the bottom. For example, the MTDNN XRNet and our recently proposed Vega V1, which focus on pushing the limit of the parameter efficiency by self-supervised learning to exploit the knowledge from a large amount of data to enhance the understanding ability of the pre-trained language models. Very unfortunately, foundation model training is costly. Shall we really put a serious effort and resource in such an expensive arms race? Hopefully, we can have some guidance from existing theoretical investigations. Although current deep learning theory is still in its infancy, we can already foresee to some certain extent the inevitable rise of super deep learning. I will now present a brief introduction of the three main dimensions of deep learning. They are deep, wide, and large. Long time ago, people questioned neural networks mainly because of two reasons. First, it is difficult to control the complexity of the networks, which are guaranteed by the universal approximation theorem. Second, the highly nonlinear neural networks have an infinite number of local solutions, and thus the local optimal solution is very sensitive to the initializations. Around the 1990s, several research groups independently proved the universal approximation theorem, that is, neural networks can approximate any continuous functions. One important result obtained by Honig is one hidden layer network has the universal approximation ability when the network is infinitely wide. So given this theorem, why should we want to have many hidden layers? According to the statistical learning theory and the strong information processing inequality introduced by information theory, we find that under the premise of a sufficiently small training error, the generalization error of the network will exponentially converge to zero as the number of network layers with information decay properties increases. Specifically, we can use a Markov model to describe a deep neural network. And so the mutual information between input and output is non-increasing as it goes through the network layer by layer. And we assume that most of the layers are actually information loss layers. This suggests the hierarchical structure in a deep network is very essential to filter out redundant information, which is not so useful for the subsequent classification. The feature mapping for each layer in deep neural networks is likely to be non-invertible, such as convolution, pooling, ReLU activation, dropout, and so on. So which results in information loss. So according to the intrinsics of all the characteristics of these layers. To a certain extent, this finding explains why we need deep neural networks. Of course, we still have to obey the principle of occurrence reason and avoid unnecessarily multiplying entities. On the other hand, the research on neural network is represented by the neural tangent kernel points out that the initialization of an infinitely wide neural network is equivalent to a Gaussian process. It also indicates that the training process of neural networks can be described by a kernel method which can guide the network to find the most optimal solution. In this study, NTK described the local dynamics of a sufficiently wide neural network, and the theory states that a sufficiently wide neural network has fewer local optimal solutions. Additionally, according to the traditional statistical learning theory, the generalizability of a model is negatively correlated with its size. In this view, the generalizability of a large model will be very poor, and it will easily overfit the training data. This is known as the curse of dimensionality. However, our recent research has shown that the generalization is guaranteed in large-scale models. We know that neural networks are very sensitive to initialization parameters, especially small-scale networks. So our theoretical analysis has shown that large-scale networks are insensitive to initialization parameters. In addition, based on the analysis of NTK, we know that a wide enough network will effectively avoid local suboptimal solutions as well. Furthermore, according to our theoretical research, training mechanisms such as pre-training plus fine-tuning have high efficiency and good adaptability. In this mechanism, a large model is pre-trained on a larger amount of training data and then fine-tuned on a small amount of downstream data to achieve very good generalizability on downstream tasks. The large model trained on massive data provides a very good initialization for fine-tuning the model on downstream tasks, enabling the model to converge to the downstream tasks effectively. Recently, there is a popular concept benign overfitting because of some empirical observations, specifically a variety of modern deep learning tasks exhibit a double distant phenomena where, as we increase the model size, performance first gets worse and then gets better. Moreover, it has been found that double distance occurs not just as a function of the model size, but also a function of the number of training epochs. Unfortunately, the most recent research suggests the double distance phenomena will disappear if we appropriately tune the hyperparameters, choose suitable regularizers, and clean the training data appropriately. Such study has a strong indication the conventional statistical learning theory still works. Our lesson is when we train models, whatever classical models or foundation models, we definitely need more data than the parameters. But how do you really consider about the number of the data points for model training is a very good question. At least we need to understand the complexity comes from the data should match that comes from the model. Labeled data are expensive, but unlabeled data are far cheaper to obtain. Unsupervised learning, which exploits unlabeled data, has achieved amazing results with the assistance of deep learning. Aurora and his collaborators provided a generalization upper bound for contrastable unsupervised representation learning, which justifies why unsupervised learning algorithms are powerful. They provided a theoretical framework by introducing latent classes and hypothesizing that semantically similar points of the subsequent tasks are sampled from the same latent class. By assuming the learner focuses on the inner product of representations of similar pairs with each other to be higher or on average than with negative samples, that prove that the learned representations can reduce sample complexity on the downstream tasks. So this is indicated by the inequality shown here. Multimodal learning has recently received intensive attention, especially since the success of DALL-E 2. We also obtained nice progress in this direction. We can generate good-looking images and videos by using only words. The reverse is also possible, but actually much easier. At the same time, we can also integrate different modalities. For example, we can use the design of a sports car to generate the design of a corresponding SUV. In fact, in addition to these interesting applications, our theoretical analysis in the past also pointed out that through multimodal learning, we can effectively improve the stability and generalizability of the model. This is mainly because multi-view or multi-modality data have not only consistent information, but also complementary information, which will help us learn the latent intact space. We show theoretically that by combining multiple views or modalities, we can obtain abundant information for latent intact space recovery. Moreover, we show that the complementarity between multiple views modalities is beneficial for the stability and also the generalization. In addition to the recent focus on multimodality or multimodal learning, multitask learning has once again caught our attention. Google's Pathway framework provides a glimpse of the bright future ahead for larger model-based multitask learning. Why does multitask learning play an important role in the era of super deep learning? It can improve model accuracy, memory efficiency, and inference speed. When compared to training tasks individually, therefore, multitask combined with deep learning has been widely used for many computer vision natural language processing tasks. The inequality here shows that by increasing the task number under the assumption that the feature structures are similar, the algorithms will be more stable and generalizing better. Specifically, Si represents the modified version of S, where one pair XY has been replaced. By increasing the task number, the difference between the hypotheses learned by S and Si will become smaller with a convergence order of 1/t. Deep learning has become an important means of achieving artificial intelligence, with its complexity and variety guiding us towards the development of foundation models. There are many reasons behind this development. Where we are on this topic, and I'd like to mention our recent book, which covers the theoretical foundations of deep learning. The book will be published by Springer soon. It covers topics of wide interests, including the relationship between model complexity and the model capacity, the role of the stochastic gradient descent algorithm as a regularizer, the geometric properties of neural network loss surface, and the hot topic of benign overfitting, and so on. Thank you for your attention. Before I explain my second argument, simpler yet refined, I think it's necessary to say how our recent foundation model ViTAE helps elevate computer vision tasks. The backbone architecture of deep learning has witnessed significant progress in the past years. With the rapid growth of computation resource and data volume, we can go beyond the traditional architectures and explore the more powerful super deep models. Then, how to fully utilize the resources and design a powerful backbone to aid various tasks becomes very important. Vision transformer is a trend. It simply treats an image as a one-dimensional sequence of real tokens, just like the way to deal with sentences as in natural language processing. Specifically, given an image as input, we first split the image into patches without overlaps, as shown here, the bottom of the figure. After that, we flatten the split patches from 2D to 1D by order, namely from left to right and from top to bottom, which is easily to be implemented by the reshape operation. Then the flattened patches are projected by linear projection layer to the feature space and adapted to the input feature dimension of the transformer model. Just like in NLP, position embeddings are added to the projected patches. After the transformer model equally treat each projected patch by simply calculating the similarity among all the patches and doing weighted sum of the projected patch during inference according to the similarity of all patches. Thus, each token can get the information from any other tokens and does not care about the distance between the tokens. Position embedding can help the transformer model to capture the order of the input token, which is necessary for the vision transformer model to capture the local structure of the images. It is also noteworthy that an extra class token is appended to the projected patch sequence, which will aggregate the feature from the projected patches during the inference and severe for the image classification task with the MLP head, as shown in the image. The work triggered the wave of transformer in computer vision community. Within 2 years, the first vision transformer paper has been cited more than 5,000 times. We can easily see there are quite a number of important subsequent developments, including the swing transformer. We wrote a survey paper which is recently accepted by HV transactions on pattern analysis and machine intelligence. I hope it is helpful for you to understand this topic. Although ViTAE obtained promising performance on image classification, it is challenging to train ViTAE. To understand this challenge, we need to revisit the inductive barriers in convolutional neural networks, which are easy to train. The successful convolutional network architectures usually include useful prior knowledge of the images within the architecture design and facilitate the training, where the modeling of prior knowledge is called the induced inductive bias. Here is an example to illustrate the two inductive biases. They are the locally correlation and the scale invariance. So they're quite popular in computer vision community. The local correlation means that the spatially adjacent pixels within the image are usually highly correlated, as shown in the blue rectangular, where the pixels around the cat's ear have similar colors and from similar and also form similar textures. The second inductive bias, I think is interesting, is the skill variance of the objects. The cat in the red rectangular and that in this yellow rectangular, they're of different size, but actually they're both cats. So the convolutional networks are capable to leverage these two inductive biases by the convolutional operation and also multi-skill architecture design, delivering promising performance. However, ViTAE simply treats an image as a one-dimensional sequence of vector tokens, lacking an inductive bias in modeling either the locality or the skill variance of the 2D images. Although it's possible for ViTAEs to learn such inductive bias from the data themselves, that usually costs a lot of training data and much longer training schedules. Therefore, practically, this is not very useful, at least for this current moment. Then a question naturally arises. So can we improve the data-hungry issue in ViTAEs by leveraging the inductive biases? The answer is positive. The two inductive biases have been widely explored in convolutional networks, but also rarely studied in vision transformers. By involving inductive bias into the transformer, we propose a model called ViTAE, or Vision Transformer, advanced by exploring intrinsic inductive biases. To model the skill variance, we resort to the across convolution layers with various dilution rates to capture features at different scales, as shown in the figure here. Also, we utilize a convolution branch in parallel to the multi-head attention module to model the locality, as shown in the figure here. There are two types of the cells designed accordingly in the proposed ViTAE model. One is the reduction cell in green, and the other is the normal cell in blue. The two types of the cells are stacked to form the whole architecture. Specifically, 3 consecutive reduction cells embedded the features to a 1/16 of the original image size. Then, several normal cells are stacked to further process the features. As shown in this figure, the reduction cell contains the across convolution layers, and the parallel convolution branch, aside from the transformer layer, the parallel convolution branch has a full stride of 4 or 2 to downsample the feature map, whereas the across convolution layers also have a stride of 4 or 2 to downsample the feature map. The convolution layers introduce the locality inductive bias, where the across the convolution layers introduce the skill invariance in hierarchy invariance inductive bias. We can show the figure here. The normal cell is very similar to the reduction cell, except that it has no across convolution layer and has a stride of 1. The convolution layer introduces the locality inductive bias, which are complementary to the multi-head self-attention layer, which is good at modeling long-range dependencies. To better fit the downstream tasks, including segmentation, detection, pose estimation, the model is required to output features of different resolutions. Therefore, we rearrange the reduction cells and normal cells in a stage-wise manner. The prediction of classification is from the average pooling of the final output feature. Although local window attention can reduce the computation and memory cost, the user predefined and fixed window partition to deal with different tasks and inputs. Such design has several drawbacks. First, for example, just like convolution, the receptive field of a single window-based transformer layer are restricted to a local window. Thus, it requires stacking multiple layers of networks to enlarge the receptive field of the deeper network. Second, the objects belonging to the same category may have different scales in the images. Directly using fixed size windows dismiss such property of object distributions and may not be conducive to handle objects of different scales. Third, different from convolution, which incorporates a sliding operation to enhance information exchange, the window-based attention partitions the images into sub-windows and conduct information exchange among the windows and ignores cross-window information. To this end, it requires cyclic window shifting to promote cross-window information exchange and model long-term dependencies. Therefore, can we make the window-based attention operation more flexible? One of the critical lessons we have learned from the success of deep learning is to turn as many things from handcrafted to learning or automatic learning as possible. Such lesson holds no matter for feature extraction or the design of the architecture of the network structures. Inspired by this motivation, can we turn this handcrafted fixed window partition into a learnable approach? So we show the diagram here, and we would like our network can dynamically determine the shapes and the size of windows based on the trained data and use the transformed windows for attention. Thus, we can model object features at different scales. Besides, since each window can flexibly determine its own size and locations, there are expected that overlaps exist between different windows. To this end, each learnable windows also can facilitate cross-window information exchange, even without heuristic cyclical window shifting operations. Then here shows the design. And also we use this figure to visualize the results. So we can compare the swing transformer and then using the ViTAE strategy. So we can find that the swing transformer cannot attend to the object appropriately, where the proposed learning-based window selection can locate to the object easily. And given this, we can largely improve the subsequent classification performance. Besides, ViTAE demonstrates good performance across a wide range of parameters, from 5 million parameters to 1 billion parameters. So ViTAE obtains continuous performance gains, implying a foundation model choice for the development of super deep learning. So we can see the trend we can see the trend easily. So next we show how ViTAE redefines the art of computer vision. So given limited time, I'm not going to provide a lot of details, but I just show some tables. And here I wanted to mention that this ViTAE Huge achieves 91.2 top-line accuracy on ImageNet real dataset, and currently is the best performer model on this dataset. And it visualizes the attention maps for different images calculated by ViTAE, and also T2T ViT. So we find that our ViTAE can locate to those objects or objects precisely. And we also find that for object detection, so ViTAE-based model is much more effective. And also for semantic segmentation, video object segmentation, and also human pose estimation. We also conduct image mapping, and the ViTAE-based model is superior to other ResNet-based models and other transformer models. We also introduce the ViTAE to syntax detection, so we can see that the model itself is very robust. And also the syntax recognition, the remote sensing applications. We trained the world's first remote sensing pre-trained model, and demonstrate that it's really effective and easily outperform existing ResNet or string-based transformer models. So we use these examples to show that the ViTAE, the foundation model, is very effective for many computer vision tasks. So we actually already explained the complexity, and we show that when we have more parameters, our model can obtain much better performance. Now I think it's time for us to return to our original intention, which is to be simple. To be both small for more is different, and simple for simpler yet refined seems to be contradictory to each other, simple and more. But the actual concept between more and simple is not contradictory. More here means that the model should be large, having a large number of parameters, while simple means that the structure of the model should be simple, despite having many parameters. Therefore, more refers to the large number of parameters in the model, and simple actually refers to the simplicity of the design concept. So in the process of exploring deep learning, so we discover that super deep models do not rely on complex functional module design to improve the network performance, but instead achieves the ultimate victory by stacking a sequence of simple model structures to achieve a large number of parameters. We need to understand the origin of complex structure design in the original convolutional network era. Due to the relatively limited amount of data available and an insufficiently large model volume, we need to design a sophisticated structure to help us quickly converge on a reasonable model from a limited sample size. However, based on the transformer architecture, we now see that through the data-driven approach to achieve intelligence, we will no longer need to carefully design complex modules. Google's related research allows that eventually we will abandon those complicated artificial designs and more towards a simple structure driven by data. although the final model will have a large number of parameters. However, presently, we still have to introduce some specific structures in the process of using transformers. In fact, the main reason for this is our data and computational resources are still limited. With the further increase in the amount of data and the further enhancement of computing power, I believe we will eventually see the road to simplicity, or simpler yet refined. I think maybe I use some examples to demonstrate the allure of foundation models simple. In the traditional convolution network design process, smart researchers have designed many different components such as group convolution, multi-skill context modeling, spatial and channel attention mechanisms, and cross-layer dense connections, so as to improve the model to learn multi-skill features, model long-range dependencies, and increase model generalizability. But this inevitably makes the network very complex and increases the training cost accordingly. In contrast, the transformer structure is very simple. By stacking transformer blocks, the network can be expanded, and the model capacity can be improved as well. Transformers can directly learn local representation capabilities, multi-skill representation capabilities, and long-distance representation capabilities from massive data directly. As can be seen from the figure here, we can see that the performance of residual network is easily statued as the model capacity increases, while the transformer has good stability, and its performance continues to improve as the model capacity increases. Because the transformer has stronger model representation capabilities, its model performance can be further improved when the available data increases. We have the same observation. So given limited time, I don't want to provide too much details for object detection, object tracking, and also pose estimation. But actually, we have the similar or nearly same observation that we need to reduce the complexity of the model design. We should try our best to keep the model or the module design as simple as possible. Here, I'd like to conclude my speech. Charles Handy, a famous management guru, was pointed out that any type of growth curve will eventually move past and will eventually pass the inflection point of the growth parabola. The secret to maintaining sustained growth is the portfolio theory, which is to predict and deploy a second new growth curve in advance before the first curve decelerates. The development of AI follows the same pattern. We know the traditional statistical learning-driven AI showed a sluggish growth around 2010. But deep learning-based AI that appeared in 2006 has injected a new vitality into AI development. In the past 10 years, deep learning has fully demonstrated its value in the development of human civilization. Its success is a testament to the deep integration of data, computing power, algorithms, and the realization of our vast capabilities. With the rapid increase and the development of data, computing power, and algorithms, the concept more is different and simpler yet refines. Illustrates the critical role of super deep learning or foundation model in breaking through the bottleneck in AI development. I believe super deep learning has the potential to elevate artificial intelligence from a quantitative change to a qualitative change. Now, I guess you may want to know more about our ViTAE model. All the related materials have been released on GitHub. And maybe I stop here. Thank you very much.
Hi, hi, Dacheng. Hi, how are you?
Good.
Yeah, it's a very comprehensive and deep talk. I would say the materials are very impressive, and yeah, it's very concise and vivid. I believe all of us are learning a lot. So we're running a little bit behind the schedule. So I have a really quick question, but it's narrowed. So since you work at JD.com, so I guess a lot of audiences, they probably wonder, is there any killer application of computer vision in e-commerce?
So actually, there are a lot. Yeah, just to give you one example. So when you purchase products from the mobile app, so you know it's based upon the large scale recommender system. So that use artificial intelligence, that use a lot of capabilities in computer vision, like recognizing those objects, like tagging those products, like how to recommend appropriate products to our customers. So also the currently JD.com, we have JD Logistics. So we have an X Lab. They have unmanned vehicles to deliver products to our customers. So they all use computer vision or artificial intelligence functions. And the current super deep models, they work very well and can provide related support to some practical applications.
All right, very good. So right, okay. So let's thank Professor Tao one more time, and thank you very much.
Okay, so thank you.
All right, bye.